Hi everyone. Today we're going to continue our discussion on chemical reactions, and we're going to start by categorizing different types of reactions. So there are many different types of chemical reactions, and we can classify them according to different characteristics of the reactions. So down below we have a nice little chart. And you'll notice that at the top we have just chemical reactions. So that's our blanket term for all reactions. And then we're dividing that into two categories, non-redox reactions and redox reactions. And we're going to discuss what that means, but you'll notice that each of those categories have subcategories associated with them. So today we'll just focus on non-redox versus redox reactions, and then in the next lecture we'll dive more into the lower categories. So let's start by defining what a redox reaction is. So the word redox is actually a combination of two words, reduction and oxidation. And these two words have multiple meanings when we apply them to chemical reactions. So on the right-hand side, there's a table you can find in your textbook, table 5.1. And this goes over common uses of the terms oxidation and reduction. So oxidation means that either something is combining with oxygen, or something is losing hydrogen, or something is losing electrons, or we have an increase in something called an oxidation number. So there are four different meanings to the term oxidation. And then reduction means that we're either losing oxygen, or we're gaining hydrogens, or we're gaining electrons, or we see a decrease in something called oxidation number. So there's four different meanings to the term reduction as well. Now, oxidation and reduction are opposite of each other. So you'll notice that, for instance, oxidation means that something is combining with oxygen, whereas reduction means something is losing oxygen. And we'll go over more of this as well. So in general, redox reactions involve a transfer of electrons between reactant molecules. So really the key meanings here have to do with electrons. Now, if something is gaining or losing oxygen or gaining or losing hydrogen, that does also involve a transfer of electrons typically. So all of these meanings are still very tightly correlated with each other. But we're going to focus mostly on the loss or gain of electrons. Now, how can we tell if something is losing or gaining electrons if we don't have, for instance, ions? What if we have covalent compounds? So we're going to use what are called oxidation numbers, which will provide a convenient way to determine if electrons are transferred. So oxidation numbers, also called oxidation states, are positive or negative numbers assigned to elements in chemical formulas according to a specific set of rules. And we're going to abbreviate the term oxidation number as ON. Now, oxidation numbers are not ionic charges. Now, sometimes oxidation numbers will look like or are very similar to ionic charges, but they're actually just made up arbitrary numbers to help us determine if something is losing electrons or gaining electrons. So again, these are not ionic charges. All right, so rule number 1. We're going to say that the oxidation number of any uncombined element is 0. So for instance, if we have an element in its pure form, then we're going to say it has an oxidation number of 0. Or another way of thinking of this is, it's a neutral element. It hasn't gained or lost electrons. So for example, if we just have pure iron, we would assign a value of 0. And then if we have pure chlorine, which exists as a diatomic molecule, we would also give that a value of 0. Or if we had pure calcium, we would give that a value of 0. And then in rule 2, we're going to say that the oxidation number of a simple ion is equal to the charge on the ion. So for instance, if we have a magnesium ion, we know that its charge is +2, so we would give it an oxidation number of +2. And then oxygen, we know, has an ionic charge of -2, so we would give that an oxidation number of -2. And chlorine, we know, has a charge of -1 when it's in its ionic form, so we would give it an oxidation number of -1. So here it looks like the oxidation numbers are the same as the ionic charges, and they are, but again, oxidation numbers are technically not ionic charges. They're just a random number we're assigning, or seemingly random, in order to determine if electrons are being transferred in a reaction. Okay, rule number 3. We're going to say that the oxidation numbers of group 1A and 2A elements, when they are in compounds, are always +1 and +2 respectively. So as an example, let's say we have sodium sulfide, Na2S. Sodium is a group 1A element, so we're going to say that it has a +1 oxidation number. Or another example, let's say we have calcium nitrate. We're going to assign calcium a +2 oxidation number because it is a group 2A element. And then rule number 4, the oxidation number of hydrogen is +1. Now there are some exceptions to this rule, but for the most part, hydrogen always has an oxidation number of +1. So as an example, if we have hydrobromic acid or hydrogen bromide, hydrogen will have a +1 oxidation number. Or if hydrogen is in a molecule like sulfuric acid, H2SO4, we're going to assign hydrogen a value of +1 as well. All right, and then rule number 5, the oxidation number of oxygen is -2. So that will always be true. Oxygen will always have an oxidation number of -2. So in water, for example, oxygen would have a value of -2. And then rule number 6, which is really important, the algebraic sum of the oxidation numbers of all atoms in a complete compound equals 0. So if we have a compound which contains multiple elements, we want all of the oxidation numbers of those elements to add up to 0. So for example, let's say we have the compound magnesium sulfate. And we saw earlier that a group 2A metal will always have an oxidation number of +2. So magnesium will have a value of +2. We also saw that oxygen will always have a value of -2 in terms of oxidation number. But what about sulfur? We didn't really see any rules about sulfur. So we're going to have to determine the oxidation number of sulfur using a little bit of math here. So far we have +2 from magnesium, and then we don't know what sulfur is, so I'll just leave that as S. And then we have 4 oxygens, and each of those oxygens has an oxidation number of -2. So we'll multiply 4 by -2. And then we want to set this equal to 0 because the overall compound has a neutral charge. So we want the overall sum of everything to add up to 0. All right, so let's simplify this. So we've got +2 plus S plus 4 times -2, which is -8. And let's see, if we simplify further, we have S plus -6, so that's -8 plus 2. And we want everything to equal 0, so that tells us that S has to equal +6. Okay. So that's how we would determine the oxidation number of an element that doesn't really have a rule assigned to it. And that can happen. So the next rule, rule number 7, the algebraic sum of the oxidation numbers of all the atoms in a polyatomic ion is equal to the charge on the ion. All right, so for instance, if you have a polyatomic ion that has a positive charge or a negative charge, we want all of the oxidation numbers for each of the elements to add up to that charge. So for example, HCO3 minus has an overall charge of -1. And we already know from our rules that hydrogen will always have a value of +1. And again, there are exceptions, but for the purpose of this class, we'll assume that's always true. And then oxygen always has a value of -2, but we don't know the oxidation number of carbon. So we need to figure that out. All right, so we have +1 for hydrogen, and I'm just going to leave carbon as it is because we don't know its oxidation number. And then we have 3 oxygens, each with a value of -2, and this should all add up to -1 because the overall charge on this polyatomic ion is -1. Quick question, what is the name of this polyatomic ion? So you should have said hydrogen carbonate or bicarbonate. Either one is correct. All right, so now let's simplify this. So we have +1 plus carbon plus 3 times -2, which is -6. And that, again, all needs to add up to -1. So let's simplify a little bit further. So -6 plus 1 is -5. So carbon will equal -1 plus 5, which is +4. All right. Now, again, the reason that we're going through all of this is so that we can apply it to a chemical reaction. So we're going to try to determine if, for instance, oxygen in the reactants is losing or gaining electrons to become something different in the products. If it does gain or lose electrons, that means we have a redox reaction. If it doesn't, that means we don't have a redox reaction. So, one more thing with redox reactions. In a redox reaction, the substance that contains an element that is oxidized is called the reducing agent. And then the substance that contains an element that is reduced is called the oxidizing agent. So it's kind of flipped, right? So let's say that something loses electrons in a reaction. We say that it is oxidized. And we can also say that it is the reducing agent. And then if something gains electrons in a reaction, it's reduced, and we would say that it is the oxidizing agent. All right, so down below we have table 5.2, and this is showing properties of oxidizing and reducing agents. So an oxidizing agent is something that gains electrons, or its oxidation number decreases, or we could also say that it's reduced. And then a reducing agent is something that loses electrons in a reaction, or its oxidation number increases, or we could also say that it is oxidized. Now, there's a couple of ways to remember whether something is oxidized or reduced. So I have a couple of acronyms here. The first one is oil rig. So that means that oxidation is loss of electrons. Reduction is gain of electrons. And then the other one is, let's see, I'll write it down below. Leo, the lion, says grr. So that stands for loss of electrons is oxidation, so LEO. And then gain of electrons is reduction, GER. So whichever one you like better, you can use that as a way to remember that something is oxidized if it loses electrons, something is reduced if it gains electrons. So now let's determine the oxidizing and reducing agents in the following reaction. Now, not every reaction is a redox reaction, but we can use these oxidation numbers to determine if electrons are transferred. So we're looking for a change in oxidation number. So first, let's assign oxidation numbers. So I'm going to write a reactants versus products table. So kind of similar to what we were doing for balancing equations, but this time we're assigning oxidation numbers. So let's start with sodium. So in the reactant, sodium is reacting with water, and then in the products, we're producing hydrogen gas and sodium hydroxide. So sodium is starting out in the reactants as a pure solid. It's just by itself. So we would assign that a value of 0. But then in the products, sodium is now combined with oxygen and hydrogen. So because it's in a compound and it's a group 1A metal, we're going to assign a value of +1. So now let's go to hydrogen. So when hydrogen is in a compound, it always has the value of +1. So in this case, in the reactants, hydrogen is in the molecule water. So we're going to give it a value of +1. And then in the products, hydrogen is actually existing in two different molecules. In the first molecule, we just have pure hydrogen gas, H2. So we would assign a value of 0. But then in the other product, sodium hydroxide, hydrogen is in a compound, so we would give it a value of +1. And then our last element is oxygen. And remember, when oxygen is in a compound, it's given the value of -2. And then in the products, oxygen is still in a compound, so it would still have the value -2. Okay, so now we want to look for any changes in oxidation numbers. So we can see that sodium went from 0 to +1 for oxidation numbers. So now we have to determine, did sodium gain electrons or did it lose electrons? So in this case, the oxidation number increased. So that means that sodium lost electrons. And remember our acronym oil rig, or Leo the Lion says GER. If we have a loss of electrons, is that oxidation or reduction? So hopefully you said oxidation. And now hydrogen, we also saw a change in oxidation numbers. So hydrogen went from +1 to 0, at least for one of the products. So is that a loss of electrons or a gain of electrons? So since we're going from +1 to 0, that means that we must have gained a negative charge because we're reducing the oxidation number from +1 to 0. So if we're gaining a negative, that means we're gaining electrons. So if hydrogen is gaining electrons, is that oxidation or reduction? So hopefully you said reduction. And in redox reactions, oxidation and reduction go hand in hand. So if something is losing electrons, something else is gaining those electrons. So if you can even just figure out one of the elements, you can then figure out the other element. So in this case, for instance, we figured out that sodium was losing electrons. So that must mean that another element is gaining electrons. Now, oxygen is our last element in this reaction, and its oxidation number did not change, so we just don't really consider that one. Okay, so now let's determine which element is the oxidizing agent and which element is the reducing agent, or rather, which compound is the reducing or oxidizing agent. So we said that sodium lost electrons, so it was oxidized. So that means that it is the reducing agent. So again, the way that I always remembered this when I was learning about redox reactions, if something was oxidized, then it's the opposite agent. So sodium is oxidized, so it's the reducing agent. And then for hydrogen, we said that H2O, or hydrogen within that molecule, gained electrons, which means it was reduced. So now it's the opposite agent. So it's the oxidizing agent. All right, so that's another point I want to make is even though we were just considering hydrogen, oh, my pen stopped working, there we go. We're actually going to consider the full molecule that hydrogen is in. So hydrogen itself gained electrons, but because it's within the molecule water, that means water is the oxidizing agent. Okay, so now that we know how to determine whether we have a redox reaction, we can also, of course, determine what is our reducing agent, what is our oxidizing agent. Again, if we didn't have a change in any of the oxidation numbers, then we would have a non-redox reaction. So now that we know how to figure out non-redox versus redox, in the next lecture, we'll go over more about different types of reactions or subcategories of redox versus non-redox reactions. So I will see you in the next video.